All right, everybody, welcome to Plasma 102, where we're just gonna finish off what we didn't cover in Plasma 101, and this is going to be delving much less into the actual plasma physics and much more into MiTEE and how the MiTEE Plasma subsystem works. So, really, the core of MiTEE is being an electrodynamic tether. So, I'm just going to take a quick second now to draw the actual circuit of MiTEE and what that looks like. Tippy toes for this one. So, this is basically what MiTEE looks like as a circuit diagram. And obviously, because it's a circuit diagram, none of this is to scale. In fact, this little block here, from the top of the picosat to this little E-shaped thing, which is our CubeSat ground, is actually the entire length of our tether. So the boom on MiTEE 1 and MiTEE 2, it's going to be like a 30-meter tether. So, fun times. So, some notes. This is our thermionic cathode. This is our repeller. And above it, we have our aperture. And beyond that, even the surrounding plasma. And the rest of what I've drawn here are fairly standard circuit symbols. So this circle with an arrow in it is a constant current power supply, and these circles with pluses and minuses in them are voltage supplies. So a current supply sets a specific current through the loop, and then voltage supplies set a specific voltage going between their two ends. Oh, and I misdrew that. Terribly sorry. That's actually what the loop looks like. So, basically what happens from the positive end is that this HVPS positive, or high voltage power supply positive, biases the picosat from 0 to 200 volts. because the picoset is surrounded by a plasma, it attracts the electrons in the plasma to it. And as soon as they hit the metal, they become part of our spacecraft, essentially. So then these electrons flow as current to ground. So if you had a voltage supply, normally you'd expect current to be going in this way, because normally in electrical engineering, we measure current by positive charge flow. So because these are electrons, and we're tracking the movement of electrons, our current is opposite to the flow of electrons. It's going down. So it's going down. Our current flow is going down through the voltage supply. The electrons are actually snaking their way up to ground. So ground is just the body of our chassis. We don't exactly have a cable running all the way to Earth ground from our satellite, because if we did, we'd have just invented a space elevator, and that's a little bit outside the scope of what we're doing. But ground's just our chassis, and it's just what we reference everything else in the spacecraft to. So ground's not really a physical entity, it's just something that somewhere we say is zero to make the math easier. And so, for instance, the processor on our system might be running off of ground, has its ground pin, and then it has a 3.3 volt power supply going to its VCC, which is what most power ports are called, VCC, and that might be 3.3 volt. So it doesn't actually need ground to be ground, it just needs a 3.3 volt difference between VCC and ground. So you could just as easily put ground up here and ground VCC and have this this node would now become negative 3.3 volts, and it still doesn't matter because to the processor all it cares about is there's a 3.3 volt difference between VCC and ground. So ground for us, we say it's the chassis just because it's easier for most of the other electronics, but the other important thing is that for us, ground is a massive pool of electrons. The chassis has a lot of free electrons that it can take some more or it can give some, and for most sensitive subsystems that involve plasma, you want to be tying your ground to the biggest body of charge that you can, so that the voltage doesn't swing too much either way. Well, that's actually probably not true, but we can go into the actual reasons you do that at a later time. So from ground, we go through the HVPS negative, which biases this whole portion of our circuit 0 to 200 volts negative of whatever ground is. And then this ammeter tracks the amount of current flowing from ground to this loop. Similarly, I didn't mention this before, but this ammeter tracks what we call I-tether, which is the amount of current that flows through the picosat to ground. So what do electrons do when they reach this loop? Thinking slightly backwards here. Electrons in this loop flow around this loop because they're being pushed through it by this constant current power supply. So this constant current power supply is just forcing things in a loop through here. If it weren't for the plasma for the plasma dynamics that we're going to be doing with our cathode, In fact, you would never actually see electrons move through this part of the circuit at all, because the CCPS just forces charge through here, and current only flows in loops, right? So without all of our plasma stuff here, then this is just a biased piece of metal, and no current actually flows through this this part of the loop. However, that's not the case for us. So, loop. We're recording it here.
Ooh.
Yeah, but when our current goes through the cathode, it heats up the cathode, and the cathode goes through a process called thermionic emission, which is where when any bit of anything gets incredibly hot, it will start to produce electrons. It will start to emit electrons from itself. So electrons come flying out of the cathode, and they either hit the aperture, which is the sort of window that we have for the cathode, that the window from the inside of the cathode's housing to the surrounding plasma, or if they don't hit the aperture, they go off into the surrounding plasma. So, if you can imagine it, we actually have a second loop, because current always travels in loops. We have a second loop that completes our circuit, going all the way from the picosat to the cathode. And
That other loop is connected to that aperture?
it goes from the cathode, not necessarily to the aperture, but to the cathode.
Okay.
So there are actually, I lied, there are actually three loops, because the aperture is attached to an ammeter, which is then directly attached to ground. So this is your third loop, is an electron hits the aperture and then returns to ground. So does that make sense so far?
Yeah.
So we have three loops. We have CCPS just running heater current through the cathode. We have electron gets emitted from the cathode and goes back to ground, and then goes to the HVPS negative and returns to this loop. And finally, we have the loop that is going to make our tether actually work. We have an electron goes out into the surrounding plasma and gets replaced by an electron from the plasma surrounding the picosat. So these are the three loops that balance our charge in MiTEE. And in equilibrium, we have two terms. I tether is equal to I out. And I out is equal to the current that, the electron current that leaves our spacecraft and goes into the surrounding plasma. So how do we calculate I out? Because we don't have an ammeter in the plasma, do we? And we really can't measure that. So we actually measure it using two terms that we know, and two strategically placed ammeters. We have I app here, which is our aperture current. This is the electron current that from an electron coming out of our cathode and hitting the aperture, then returning to ground. And then we have IK, which is our emitted current. So our total emitted current is everything that leaves the cathode. Our aperture current is the portion of the emitted current that hits the aperture and does not leave our spacecraft. So I out is equal to IK minus I aperture. So once we have our I out, then we know our tether current should be, theoretically, in equilibrium. So what happens when these two are not equal, when this system is not in equilibrium? Well, this is when we start to charge our spacecraft in the plasma. And this is exactly the same kind of electrostatic charging that you get with like a Van de Graaff generator, or you get with a just rubbing a balloon on a wall. One becomes negative, and on Earth, one of your objects would become positive, but here we're in a plasma, so the plasma will kind of self-shield from that, as you learned in Plasma 101. So when our charges, let's say, for example, I tether becomes larger than I out. So that means we're collecting more electrons on the picosat than we're emitting from the cathode. So if we get too much electron current, what's going to happen?
It won't be able to emit all of them at the time, so...
well, it's already not emitting. We're already emitting less than we are
so
collecting.
The bias will change so that you're not collecting as many? Or?
Yes, the spacecraft will charge negative. Because you have more electrons now than you do protons. So your whole spacecraft charges negative with respect to the plasma that surrounds it. So our whole spacecraft is in a soup of plasma, and now ground isn't our spacecraft ground isn't close to the plasma potential. It actually starts drifting away negative. So this is a problem for us because the picosat actually doesn't care about what our spacecraft potential is. We can only set it like what its voltage is by setting it as a difference between our spacecraft and the picosat. But in terms of electron collection, it actually matters what the voltage difference is between the picosat and the surrounding plasma. So let's say that we charge 50 volts negative. So our V spacecraft common, which is another way of saying ground, is equal to V plasma minus 50. So if our hang on, I'm just getting a call. If our picosat, V pico, is equal to VCC plus 200, then V picosat minus V plasma is equal to 150 volts. So now that the picosat is only 150 volts, as opposed to like 200 volts at its maximum setting, then it's not going to be collecting as much charge. So your I tether is going to drop. And your I tether is actually going to drop until you reach equilibrium again. And equilibrium will happen not necessarily when ground reaches zero, but just when these two currents are the same. So you'll be in equilibrium, but you'll be at like negative 50 volts with respect to the plasma. So, I mean, the same thing will happen if you do the opposite, if you start charging positive. If you start charging positive, the picosat will collect less. And actually something I haven't mentioned so far is that the cathode will, in some cases, emit more. If the cathode's in a regime where it's limited by the electric field between the cathode and the surrounding plasma. We'll talk about that in just a second. So that's basically how our tether works. Does that make sense to everyone? Okay, we'll just go over some cathode basics then. And that will wrap up our learning session for today. So, I haven't mentioned so far on the circuit the repeller. I haven't really covered the aperture in too much depth. And that's because these make a lot more sense once you know what the cathode kind of looks like. So the cathode housing, this would just be a 2D slice of this. The cathode housing looks something like this. Just got some wires coming out the back.
Hello.
Hello, Derek. We're recording.
Oh, fun. I'm gonna go find Joe first and then.
Okay. So this is the aperture. This is plasma. This is your filament, which is just kind of like, the filament is literally like a light bulb filament. It's actually constructed very similarly to one, except for a couple changes. And then you have a repeller. So, as I mentioned, our cathode is a thermionic emitter. So that means that we get this filament to about roughly 10,000, no, not 10,000, that would be way too hot. Roughly 1,000 degrees C, or about 1,300 Kelvin. Here, the sort of darker material that I've drew in is Maycore, which is just a machinable ceramic. And the important thing is that it's an insulator, both electrically and thermally, so that your repeller and your filament don't touch your aperture, which is the metallic housing that this whole thing is covered in. So, with thermionic emission, the thing is that I said your electrons basically get boiled off by the heat. However, just kind of like, if you think about it like a pot of boiling water, actually boiling water is a bad metaphor for this, so I'll just stop trying to do metaphors. If your electron tries to come out of the filament, unless you have a very strong motivating field, it will pop right back into the filament and you won't actually see any emission. It's leaping out for a second, but it's just hopping right back down. So, in order to overcome this effect, we need to create an electric field that's going to motivate these electrons away from the cathode. And this is why we have our HVPS negative over there. So we ground the aperture. We set this 0 to negative 200 volts. And we set the repeller to be 20 volts below that. So our repeller goes to negative 220 volts. So I generate a pretty massive electric field in here, for our applications at least, where your field lines are pointing in. And because electrons are negative charge carriers, electrons will move opposite to the field lines. So when one jumps out of here, an electron will start flying away into the surrounding plasma. Or it will hit the aperture. So what does the repeller do? The repeller is just there to make sure that our electrons are focused, like our electron beam is focused towards the aperture. So you can see it's very concave, and that's so that your field lines, you're essentially blocking off your electrons from going backwards and towards the sides of the aperture by creating a strong negative potential here. This is going to slightly decrease your overall emission, but it's not going to, it's going to increase your overall eye out in the end, just because your beam is so much more focused. So there's another effect other than the that causes the electrons to leak back into the filament that I haven't mentioned yet, and that's something called the space charge limit. So the space charge limit basically says, I'm going to draw another of these little stylized guys for this demonstration. The space charge limit basically says if I have a bunch of current flowing through a space, like say these emitted electrons, then on an instant-by-instant basis, you can just picture these electrons as a cloud that's just sort of hanging there. You don't need to really think about their motion too much, at least for our application. So when an electron tries to jump out of the cathode, this field of electrons basically acts as a huge negative cloud that forces it back into the cathode. So in order to overcome this space charge limit, we call it, we need to create more of an electric field so that we clear this stuff out of here faster, so that on an instant-by-instant basis, we actually lower the density of this electron cloud. So, sorry, just getting texts from Wes, so I should respond to those soon. We have two regimes with the cathode. We have what we call a space charge limited regime, and we have a thermionic emission, a limited regime. So in the end, the graph kind of looks like this. Very interested to see if you can see this on video later. If this is 0 volts and this is negative 200 volts, then you're kind of going to have a graph that looks like this. This is around 100 volts. This is about 40 volts. Not exactly to scale. And these should both have negatives in front of them. So this is our space charge limited regime. And this is our thermionic limited regime, or our heat limited regime. So the nice thing about this is that for this region of space, we actually do have a very controllable amount of emission current. And it's almost linear, which is really good for us because we want to be able to match the tether current as closely as we can. However, to avoid any of those charging effects. However, for this period of space, we're dragging everything out that we can out of the cathode. And so if we wanted to increase this amount of current from here, we would need to increase the heat. However, it's much better to control via this voltage and the space charge effect than it is via heat, just because the actual thermodynamic emission equation says, and you guys do not need to memorize this, just keep the general trends in mind, that J, which is your current density of emission coming off of the cathode, is equal to a constant, A, called the Richardson's constant, times T squared, times 3 to T to some power. I will correct that for you guys later. I think it's squared for the moment though. Times E to the negative phi over kT. So phi is the work function of your material. It's how easily that material gives up electrons. And kT is the Boltzmann constant, K, which is just another constant that you can plug in after you look it up on Google, and times UT. So if you look at this equation for the thermionic limit of this cathode, you'll see that it's varying both quadratically and exponentially. So if you make a tiny difference, like say 50 degrees, which on the scale that we're talking about is tiny, then you're going to get a huge change in current, so it's not very controllable. Whereas this space charge limit is very controllable, and that's why we set our emission current using space charge limit instead of heat. I think that about wraps up everything. You guys have learned about Langley probes. You guys have learned about the picosat, which is basically a square pizza box shaped Langley probe that no one's really characterized yet. And you guys have learned about the cathode. And now you guys have learned about our entire tether circuit. So that's about going to wrap it up for MiTEE Plasma 102, and thank you both of you. Do we have any questions?
So in the cathode, the goal is to get the electrons to hit the atmosphere?
Actually, no. The goal is to get electrons into the surrounding plasma.
And avoid the aperture.
Avoid the aperture as much as possible. And this is why we have our repeller charged negative, so we focus that beam up and out. Instead, if we wanted them to just at the aperture, we would just make this positive and surround it with metal. Yeah. The only current on MiTEE that is actually going to affect our sort of tether and affect our charging characteristics is going to be that which goes into the surrounding plasma. So only current that goes through this loop is going to affect our plasma dynamics.
So the HVPS positive and below is what is actually on the tether?
Yes.
Okay.
In fact, if you wanted to be a real stickler for it, it's that ammeter and below.
Okay.
All of this does, like everything here actually contributes to the tether because, like in a small way, but all of this is sort of sandwiched between like probably 5 centimeters vertically, whereas from the aperture down to the picosat is going to be 1 meter on MiTEE 1 and 30 meters on MiTEE 2. Does that make sense?
Mm-hmm.
Okay.
So what does it make a difference if, like, since it's so long, if there's like different electron densities in different areas, will that affect anything?
It would, but we generally don't need to worry about that because we're flying through a quasi-neutral plasma. So we generally assume that it's going to be a very evenly distributed mix of electrons and ions. The only thing that is going to change that is if you have a plasma sheath. So as we mentioned back in Plasma 101, when you charge an object, it's going to get a bunch of surrounding charge to sort of mask the charge's effects from the rest of the plasma when it's in a quasi-neutral state. But that's also kind of why we try and isolate our sheaths from one another in MiTEE, because our picosat is on a 1 meter boom. Its sheath isn't going to interact with the spacecraft sheath, and that's also the reason that the Langmuir probe is 10 centimeters away from the rest of our spacecraft, because we don't want their sheaths interacting as well. So when you don't have like any sheath interference, you can basically treat it as if you were going through a very homogeneous plasma.
And where did you get the 15, 200, and 150? Is that just because?
That's just an arbitrary example. We could charge anywhere from, just off the top of my head, 0 to 100 volts in the plasma.
So none of that bottom portion would flow if we weren't in plasma, right?
Yes.
Okay.
Which is just kind of like, you can, if you weren't in a plasma, you can try this out with MiTEE right now, if you hooked everything up. If you just bias something in air, it's going to have a voltage on it, but current isn't going to flow because you don't have those electrons moving in and out.
So how do you test that then?
So thermionic emission doesn't rely on having a surrounding plasma. So we can test our electron emitter very thoroughly, as long as we give it a supply of electrons to draw from, which in our case is ground. And when we test this on the ground, we actually don't have a plasma to fire into, so we just put another sheet of metal blocking the aperture about an inch away.
Oh, with the dark mark on it that I saw.
Yes, that was the piece of molybdenum that was discolored slightly. I'll show you that later today. And that part we can test very thoroughly. Both the Langmuir probe and the picosat you would need to test by generating a plasma in a vacuum chamber. For Langmuir probes, there's been a huge body of work doing that. In fact, I'm going to be doing some Langmuir probe tests in lab coming up in a couple weeks for my plasma course. For the picosat, nobody has, one person has tested picosats, these pizza box shaped pieces of metal in a plasma, and that was most of Iverson Bell's thesis, which is what we base MiTEE around. The science objective of MiTEE 1 is to confirm in low Earth orbit the current collection capabilities of these picosatellites. And then MiTEE 2 is going to be using that science that we've confirmed. What does it look like? So can we actually use that science to build the tether? All right. Any other questions? All right. Well, that is a wrap on Plasma 102. Thank you, guys.